Welcome to lecture number 37 for ECE 4621 Control Systems, Gain and Lead Compensation with Bode plots. Now, what we talked about in our last lecture was gain compensation with Nichols charts. Nichols charts are extremely useful. They kind of show you what's happening. I want to keep away from -1. If my open loop gain versus frequency passes through -1, the closed loop gain is infinity, so I've got to keep away. And if I want to keep the resonance less than some threshold, like 6 dB, the M circle tells me the keep away region, the points I have to keep away from. So what I do is I just G times K slide up and down until I'm stable. The gain is less than 1 when the phase is 180 degrees, and I'm tangent to the M circle. So that's what you do with the Nichols chart. Kind of a useful way to design a gain compensator. The problem with Nichols charts is they're really hard to use. They're difficult to draw, way better now that we have MATLAB, but they're still kind of painful to draw. The resonance frequency is hard to figure out because I'm trying to find out which point is tangent to the M circle, and tangent points are kind of hard to see. It'd be nice if there was a simpler way to do that. That's where we come up with the concept of phase margin in Bode plots. Now the observation is that the gain margin doesn't really tell me much. It tells me I'm stable, but this point is so far away from the resonance, it doesn't really help. On the other hand, if I look at this point right here, when the open loop gain is 0 dB, how far away am I from 180 degrees? That's almost the same thing as the resonance, and that's not true for all systems, but most systems, these 2 points are very close. So a reasonable approximation would be to say, let's assume my resonance is right here, when the open loop gain is 0 dB. Design your gain compensator so that at 0 dB, I hit the M circle. Now when you do that, I'm actually going to be a little bit aggressive. If I intersect the M circle right here, it'll actually pass slightly inside that M region. So the actual resonance is going to be slightly higher than 6 dB. That's in contrast to root locus. Root locus is inherently conservative. The extra poles make the resonance slightly less than I expect. If I design for a phase margin, that we'll be doing here, I'll have a gain that's slightly too high. The best way to do it, of course, is the hardest. You design for a resonance like using a Nichols chart. That's the most accurate, but again, harder way to do it. So to design for a phase margin, I have to be able to relate phase margin to resonance. The assumption is that I'm going to have the resonance right here. The open loop gain is 1 when the closed loop gain is the maximum. So the closed loop gain is just G over 1 plus G. I know the gain is 1 because that's my assumption. The phase I don't know. Find the phase so that the resonance is M sub M. Doing some trig identities, let's flip it. The magnitude of 1, the numerator is just 1, so ignore it. Magnitude of 1 plus phi is the magnitude of 1 plus cosine phi plus j sine phi is 1 over M sub M. Take the magnitude squared. That would be real part squared plus complex part squared is 1 over magnitude, 1 over M sub M squared. Multiplying it out, cosine squared plus sine squared is 1. Gives me 2 plus 2 cosine phi is 1 over the resonance squared. That's the equation that relates phase to resonance. That phi that we calculate is actually this angle. That's the open loop phase when the gain is 1. The phase margin is that distance to -1. And actually there's two solutions. I get minus 151 degrees in this case and plus 151 degrees. The one over here is a straight solution. I don't want that one because if I intersect the M circle right here, I'll actually be unstable. I want the negative angle. So if I want to design for a phase margin, what I would do is given G of S, and if I want to have a resonance being 6 dB, what I do is I translate 6 dB resonance to phase. And throwing it in this equation, I wind up with minus 151.04 degrees. So that's this point on the Nichols chart. The M circle intersects the 0 dB curve at minus 151.04 degrees. Or I want a 28.96 degree phase margin. The next step is to search. What frequency of G of S has a phase shift of minus 151.04 degrees? And here you guess again, guess again. Personally, I throw it on a solver on my calculator and iterate until the angle is equal to minus 151. Beep when you're done. And it comes up with 5.2362 radians per second. I want the gain to be 1 at that frequency, so K is just whenever the gain. Okay, this is really similar to root locus. At root locus, I want to find out G times K is 1 at minus 180 degrees. Pick K to make the gain 1. On a Bode plot, I want G times K to be 1 at minus 151 degrees for resonance of 2. Find that frequency, find the point on the J omega axis, and then pick K to make the gain 1. So K is 0.3926. If I draw that on a Nichols chart, notice what happens. Right here, kind of hard to see, but right there I intersect the M circle, and I actually go slightly inside of it. So the actual resonance is going to be slightly higher than 2. That's typical when you design for phase margin. I'm going to have a gain that's a little bit too high. Close, but just a little high. The resulting closed loop system then is I've got K of S, just to gain K. I've got the resonant frequency. I've got the phase margin, the resonance, it's actually going to be a little bit higher, and the closed loop dominant pole. This one I get from the 0 dB gain frequency. The complex part of the dominant pole is roughly the 0 dB gain frequency. The real part comes from zeta. M sub m tells me zeta, which tells me the angle of the pole, which tells me the real part. Suppose I want to do that on a Bode plot. Again, the Nichols charts are kind of useful, but they're painful to use. I don't really need to use a Nichols chart. If I want to design for resonance of 6 dB, I first convert that to a phase margin. I want the phase to be minus 151.04 degrees. At that point, that's the point that's too close to minus 1 on the Nichols chart. Get up here. That's this point right here. I've got to keep that point away from minus 1. So that's the point where I make the gain 1. So in your Bode plot, I look at the phase diagram, phase plot, and find out which point has a phase shift of minus 151.04 degrees. That's right here. At that frequency, make the gain 1. So go up to the gain plot. Currently the gain is 7 dB, so I want K to be minus 7 dB. I want to bring the curve down so it's 1. Gain is 1 at that frequency. And there's my design. Again, way easier. All I have to do is know the phase shift that I want. This is my phase margin. I want to keep that far away from 180. Make the gain 1 when I'm 29 degrees away from 180. So that's gain compensation. Much easier way to do it. Now let's look at lead compensation. The purpose of a lead compensator is to push the Nichols chart away from minus 1. To do that, I add phase lead, hence the name lead compensator. That's good. A side light is I'll add gain. Gain is bad. Again, back on a Nichols chart, if I add phase, that's going to push this to the right. That's good. If I push it up, that's bad. That pushes me towards minus 1. That leads into the design of a lead compensator. If I take a generic lead compensator, say 10 S plus A over S plus 10A, that 10 just makes the DC gain 1. Again, somewhat arbitrary. What happens is the gain of this system starts out at 1. At A, it increases by 20 dB per decade. At 10A, it drops 20 dB per decade. So I get this gain curve. Okay, the gain I don't like. The gain pushes me towards minus 1. That's bad. The phase, on the other hand, it starts out at 0 degrees and increases to about 57 degrees and goes back down. This is the phase lead. That's positive phase. Positive phase pushes you away from minus 1. That's the good part. So what I want to do is take that resonance point, that 5 radians per second, and put it somewhere where I add phase but not gain. For example, suppose I take the 0 and make it really, really large, meaning if 5 radians per second is over here and A is 50 radians per second. I haven't done anything. I've added a little bit of phase. That's good. I haven't added much gain. That's also good. Or I should say it's negligibly bad, because gain's bad. So I really haven't done much. If I go over here, make A too small, if this is 5 radians per second, and I make A like 0.2, then what happens is I've added not much phase, but I have added a lot of gain. That'll make me go unstable. That'll push me towards -1. The sweet spot is right here. If I pick the 0 to be 1 to 3 times my resonant frequency, I've added phase and not much gain. 1 times is right here. I've added a lot of phase, which is good, a little bit of gain, which is bad, but the phase kind of compensates for the little bit of bad. Over here I've added less gain but less phase, so it's really kind of up to you. That's where the rule of thumb 1 to 3 times comes into play. Pick the 0 1 to 3 times your resonant frequency. As an example, going back to the system that we had before, if I design a gain compensator, I'd like to crank up the gain as much as I can, but I can't go too far because I start to resonate right here at 5 radians per second. So what that means is I need to add a lead compensator. Pick the 0 to be 1 to 3 times by resonance, 1 to 3 times 5 radians per second, and let's just pick the number 6. If I add the lead compensator, this is now the Nichols chart. I took the original curve and pushed it right. That's good. What that did is that reduced or increased my phase margin, reduces the oscillation, reduces the overshoot. That's what a lead compensator does. If I have a system with overshoot at a lead compensator, the overshoot goes away, meaning I increase the phase margin. Now that I've increased the phase margin, I can crank up the gain even more. And what happens is, as I crank up the gain, I get better tracking, a faster system, because this point is now higher frequency, all the good things in life. So add the lead compensator, calculate the new system, find out the new frequency, where the phase shift is -151 degrees, and again just did a guess again numerical solution. Notice this is 3 times higher in frequency, meaning the closed loop system's got 3 times the bandwidth, 3 times as quick, 1/3 the settling time. Gain is wrong. I want the gain to be 1 when the phase is -151 degrees, so K is just 1 over the gain. K is 14.62. So there's my lead compensator. I can see that on the Bode plot as well. If I take the original curve, that's the blue line. If I want a 152 degree or 28 degree phase margin, I look at -151, -152 degrees, find out what frequency has a phase shift to -151 degrees. At that frequency, make the gain 1. To add a lead compensator, I've got phase problems at this point. Design a lead compensator that adds phase, so let's make that S plus 6 over S plus 60. What that does is that takes this phase curve and pushes it up, adds phase lead, hence the name lead compensator. It also takes the gain curve and pushes it up as well. Once I've added the lead compensator, I now find out now what frequency has a phase shift to -151 degrees. That's 17 radians per second. At that point, make the gain 1. The net result then is if I look at the lead versus lead plus gain, lead compensator increases the phase margin. The lead plus gain increases the error constant, gives you better tracking, and pushes out the 0 dB gain frequency, gives you wider bandwidth, faster system. So for example, the gain compensator that we started with last week, or last lecture, gives you a 0 dB gain frequency of 5 radians per second and an error constant of 7.85. Add the lead compensator, that does nothing for the error constant, but I reduced the overshoot, increased the phase margin significantly. And you can see that in the closed loop dominant pole. Not obvious, but if you calculate what it is, the oscillations dropped off. I now have no overshoot. If I crank up the gain, do a lead plus gain compensator, I now have a much higher DC gain, meaning better tracking. I've got a wider bandwidth, and my poles have shifted out. So lead plus gain kind of gives you everything you want. Better tracking, faster system, same phase margin, kind of by definition. So that's kind of the idea of a gain plus lead compensator. There is a shortcut for designing lead compensators. What you could do is use the Nichols chart or Bode diagram, find out what frequency is too close to 180 degrees, pick the 0 to be 1 to 3 times that. If you already know the transfer function, you kind of know what the answer is. This pull at s equals 0 I want to keep. That makes it type 1. This pull at minus 5 is causing trouble. That slows down the root locus. That limits the bandwidth in the frequency domain. Let's get rid of it. Let's put the 0 right on top of it, cancel it, move it 10 times further out. That's going to give you the same answer that we did before. The long-winded way that we just did said put the 0 somewhere between 5.2 and 15.6. And oddly enough, that's in the region or pretty close to it. If you're going to miss, it just kind of says miss on the high side, maybe s plus 6. I can also design a lead compensator by inspection. And this is where frequency domain is really nice. Suppose I had this step response. I closed the feedback loop, I adjusted K until I got 20% overshoot, and that's what I got. Okay, now design the lead compensator. From a root locus standpoint, I don't really know what to do. From a frequency domain standpoint, it's actually kind of obvious. My step input has all frequencies, the frequency contents 1 over s. The output has a pretty strong component right here at 2 radians per second. I can see that oscillation. What that means is I'm too close to minus 1 at 2 radians per second. What I need to do is add phase lead at 2 radians per second. So add a lead compensator that adds phase at 2 radians per second. Pick the 0 to be 1 to 3 times 2. I just chose 1, so there's my lead compensator. With that, the overshoot will disappear, add some gain, and I can get a faster system, better tracking, and get my overshoot back. That's kind of a story that I remember from Dr. Cowan when I took this. Dr. Cowan was doing consulting at a way station, and when the trucks came in, the needle would bounce back and forth a couple times and settle out. And they kind of asked him, can you speed that up? And sure, that's all the information you really need. Just measure that frequency of oscillation. That tells me the point where I've got too much, or I'm too close to minus 1. Add lead at that frequency. Pop in a lead compensator, and suddenly the needle stops oscillating. Add a little bit of gain, and I get a quicker response. With actually, almost by inspection. Kind of the story behind that one then is that, well, the operators were saying that, well, it's not very accurate, and had to ask them, what does accurate mean? Well, it's not bouncing. So that, well, sure, yeah, I can make it bounce if you want, detune it, but sure, if that's what you want. And that's something that you can do just by inspection, looking at the frequency domain. Just given the step response, I know where the lead compensator belongs. So with that, we have lecture number 37, gain a lead compensator design from the frequency domain standpoint.